Well, that last video cut me off for some reason, and of course I kept writing and I kept talking because I didn't know that the recording had stopped. So I have everything all written out. I'm not sure exactly where I stopped talking along here. I know I had a little bit going on with the left, but this is a very similar idea to taking a left-hand limit of a function and taking a right-hand limit of a function. So I was kind of drawing this picture in as we were going. So here's the piecewise function that we're looking at. It takes on the shape of the parabola x squared over to the left, so that's this half right here, and then it takes on the line 2x over to the right. So those are the two pieces. And so the left-hand limit, you're still doing this exact same limit derivative, just like this, or like this. Either you're coming in from the left, though, or you're coming in from the right. And so as you're coming in from the left, we still want it to do 0, and so we're looking at the point x equals 0. So we go from 0 plus h to 0, plug everything in like this. So careful here, this 0 and this 0 are different. The reason we're using a 0 here is because x is approaching 0 from the left. We're using 0 here because h is always approaching 0. So we plug this in, we've got 0 plus h squared, which of course is just an h squared, minus 0 still leaves us with an h squared. I forgot my limit clause right here, so I tried to sneak it in. This h in the denominator, h squared over h gives me h, and so with this just left as an h, as h approaches 0, I can just plug my 0 in and I get 0. So if you're looking at the picture, what this is showing is that as I move towards 0, as I'm coming in from the left, the slope of this parabola is approaching 0, which you can see. I mean, we've got kind of a steepish negative slope, and then it gets less steep and less steep until the slope is 0, and that's what happens at the very bottom of the parabola. But then from that point on, it takes on a new shape, and so as you're coming in from the right, you plug 0 plus h and 0 into my function 2x. And so here you plug in the 0 plus h minus what we get when you plug in 0. So this whole numerator just simplifies to a 2h, because of course the 0 doesn't do anything, and 0 plus h is just h. So we've got 2h over h. The h over h will reduce down to just 2, and then this is like that limit rule where we know if this is just a constant, then it's just a horizontal line, and so as h approaches anything, the value would just be 2. So what that's saying is that this right-hand piece has a slope of 2 as x approaches 0, which we know it's a linear function. We know it has a slope of 2 the entire time. So constant slope of 2 from the right, approaching the slope of 0 from the left, what we'd say is actually very similar to the limit as, I'm sorry, like a left-hand limit not equaling a right-hand limit. Since the left-hand derivative doesn't equal the right-hand derivative, we say that the function doesn't have a derivative at x equals 0. Or what we're going to talk about in the next couple of days, we'd say that f is not differentiable at x equals 0.